Hi everyone, welcome to part 2 of lecture 10. And in this lecture, we will discover the continuous case in terms of joint probability distributions. Okay. So remember from the first part, we seen that how we can calculate the marginal PDF, the joint probability mass function, etc. And the logic here and the key idea is the same. That's mean if you understand the logic behind the joint probability distribution for the continuous case, that will be easy to apply any kind of problem. Okay, so maybe the math behind these things, or to make things more concrete in terms of math, can be a little bit confusing, but I will try to make it simple so you can you can just understand it. So assume that we have two random variables. These are the continuous ones. So I can give an example. Let's say you visit a doctor and they did two tests, and these are the results of the tests, and they are the continuous. Okay, so when I say random variables, I meant something like that. So the calculating probabilities of events, if that events involve only one of them, say x, that was easy, right? Because we began with defining a function f of x, and we call this the PDF, which is greater than or equal to 0 at every point x in the range of random variable x. So please try to understand the analogy between the small x and the capital X. The small x is the values, or are the values that the capital X can take. Okay, please try to understand this one. So we call that function the probability density function, as I said here, which is called the f of x. If I want to calculate the PDF of x, the f of x, which will be the equal to the derivative of the f of x. What was the f of x? That was the CDF. So the cumulative distribution function, okay? And which is, remember that the f of x simply is the probability of x will be less than or equal to the small x. So what I mean, let's say we have a random variables, something like that, or which is the CDF of a random variables, and it takes some values, right? So that CDF shows, let's say, which is x, if this region show that the probability of x less than or equal to x. Okay, if that is x3, I can say the probability of x less than or equal to 3 is this region. So which is the logic behind the CDF. So and which is actually in CDF, I want to calculate the probability of x is less than something or equal to some value, but the PDF is the exactly one single number, right? Like which is, let's say, the probability of x is equal to 3. But so because that is not the discrete case, it's not possible to calculate the area on the x, right? Just because just that there is just one dimension, so I cannot calculate the area at that point. Instead, remember that I show this strategy. Let me clear that one. Let's say that is the x point, okay, and which is something like that. Sorry. Okay. Okay, let's make it better. Okay. So I have x, and there is only one single line. So it is not possible to calculate the area of this line. Instead, I can take the epsilon values, okay, and I can create some rectangle here, and I can calculate the area of this rectangle. And if this epsilon is very close to 0, that will be much better approximation, right? So actually, I can show this idea in terms of math. The probability of x, probability of this capital S x will be greater than or equal to x and less than or equal to x plus epsilon. Okay, so this region. And the limit of this probability when the epsilon goes to 0 will be much better approximation, right? Or the PDF or times the epsilon, okay, will give me this one, and which is equal to the CDF. Okay, so that is the basic logic when we talk about the CDF. Okay, so calculate the probability of any event with the probability of x, which takes the values from a is any event, is simply integration of the PDF for each x values that's from the event A. Okay, so you will remember this from the previous lectures. And also we have the normalization axioms, all possible x values, the integration of all possible x values will be 1. Okay, so that is for the single random variables, and we've seen these things in the previous lectures. Okay, now let's look at two random variables, two continuous random variables. Actually, we will follow the same steps. First, we begin by defining a function f of x and y, which will be greater than or equal to 0 at every point x and y, where x is in the range of x and y is in the range of y. Okay, so in a single random variables, we are looking at x, and x, that small x takes the values from the capital X, right? But now we have two random variables, the x and y, and x is taking the values from the capital X and y is taking the values from the capital Y. Okay, we call that function. So that's mean these two random variables have some common region, right? And that common region actually is called the joint probability density function of f of x and y. So please try to just imagine two distributions and intersect with them. There will be some common region, and I can represent that common region with the joint probability density function, and that is shown as f of x and y. Okay, and the same thing, the f of x and y, actually, the probability of x will be greater than or equal to small x, will be less than or equal to x plus epsilon 1, and the intersect with the y, which is greater than or equal to small y, will be less than or equal to y plus epsilon 2. Why? Because I cannot calculate, I cannot say here the y is equal to y, okay? Because just remember from this one. So I will simply do this logic for two random variables. Okay. And also I can calculate the probability of any event. In this case, the event is a pair of random variables, x and y, and these are coming from an event, okay, which is the integration of f of x, the PDF, in terms of dx and dy, because we have two random variables. And the same thing, we have the normalization axioms here, the all possible pair of x and y. If we integrate for all possible x and y, we will end up with 1. That's mean that the probability of that common region or the area under that common region will be 1. Actually, I'm saying the area, but that is actually the volume, okay? Because or yeah, area or the volume will be same. If we have two random variables, we will have two dimensions, so that will be area. We have, if we have 3 random variables, that will be the volume, okay? So try to understand the logic behind this idea. So that is for the one single random variables, right? Let's say I can say that the probability of x will be less than or equal to some x values is here. So that will be the error actually. Okay, that will be the error. But now these two guys will create a 3D shape, right? So that's why I have to calculate the volume behind this shape. So the idea is actually the similar. Now I will just apply that strategies for 2 random variables, and that 2 random variables will create a shape something like that. Okay, that can be any shape like that, but this is just an example. So I have to calculate the area. I have to calculate the volume under some specific values if I want to calculate the specific probabilities. Okay. So what I mean, if I want to calculate the probability of, let's say, the x and y is -2 and -2 and 2, I have to calculate like the volume under this region, okay? And the total volume under all region is 1. So the idea is similar. So remember from the previous part, we can calculate the marginal PMF of x and y, and the same thing here. If we know the f of x and y, okay, joint probability density function, we can obtain the f of x and f of y. Actually, the logic is same. In the discrete case, we will have 2 summation, and we will fix one of them. Remember that. Let's say the x and y, okay, 1, 2, 1, 2, 3, and let's say that is 1, 2, 3, and 4. For x, 1, y will be 1 and 2. For 2, 3, for 3, that will be 4. So let's say that is just an example. If I want to calculate the PDF of x, remember what was the PDF of or PMF of x, let's say that is the discrete. So that will give me the probability for each possible x values, right? What was I am doing? I'm fixing the x values and go over all possible y values, right? If I fix the x, what will be the y? 1 and 2. If I fix x to do 2, the y can take 3. If I fix the x to the 3, the y can take 4, right? So the same logic here. The differences, y can take the discrete values, but in this case, y can take the infinite values, right? If I fix the x to some values, y can take the infinite values. That's why instead of summation, I will use the integration, okay? So for any A, which is the event, we have the probability of x in A, okay? Actually, that is saying the probability of x in A and y in infinite values. The same logic here, okay? I will fix the x, and I will look at all possible y values for that fixed x values, okay? And that is the 2 integration, one for the y and one for the x. X is in A and the y is infinite, which is the f of x and y and dy dx, okay? So we know that one, that is the probability of any event, and which is simply the integration of the PDF for all possible x values that coming from a specific events. So let's look at here. That is equal to that one, right? That's mean this guy equal to that guy. So notice that if these two is same, I can say that on this part is actually this guy, right? F of x. So what I can say, the f of x, which is equal to the integration of f of x and y dy. Okay, and similarly, if I change the variables, I will get f of y is the integration of f of x and y dx. Okay, and the logic is same. I'm fixing the x values and go over all possible y values. And here I'm fixing the y values and go over all possible x values. And they are referred to as the marginal, the PDF of x and y respectively. Okay, so if you're confused about these things, you can just try to understand that this one, that's fine. Just understand the basic logic, okay? As we did in the discrete case. I gave the example here, like x is 1, 2, 3, and y is 1, 2, 3, 4, and I have fixed the x and look at the possible y values. Because they are discrete, they can take some limited values, but the y in the continuous case, I will fix the x, and y can take the infinite values. Okay, that is the only differences. So let's look at some expected value rule. Recall that we don't have to compute the distribution of x to calculate the expected value of g of x, right? G is a function of x, so I don't need to calculate the distribution of x. So what I mean, the expected value of g of x for the discrete case, that will be the summation of g of x times corresponding probabilities of x. If the x is continuous, the expected value of g of x will be the integration of g of x times f of x dx for all possible x values. Okay, that is the expected value rule for the single random variables. And the same thing here, this feature extends to bivariate or multivariate with more than 2 random variables case when calculating the expected value of g of x and y. So the expected value of g of x and y will be for the discrete, if x and y is discrete, that will be the 2 summation g of x and y times the corresponding probabilities. Okay, so and for the continuous case, that will be the integration of double integration for x and y, g of x and y times f of x and y, and dy dx. Okay, the logic is the same actually. So same thing with it here. We don't need to calculate the distribution of x again, just you can use the g of x and the corresponding probability of x. What I mean, for example, let's look at the here. If I want to, let's say x is take only 1 and 2, okay? So what will we do for the g of x? You will just put x values and y values, 1 and 2, and you will calculate the value of g of x and y, and also from the joint probability distributions or joint probability mass functions, you will look at the probability of x is 1 and y is 2, and you will put that values here, and you will come up with the expected value. Okay, so the logic is the same, and just as I said, try to understand the logic. So an important simplification can be obtained when G is linear. G is linear, okay? So let's say G of x and y, which is equal to ax plus by and plus c. So this function is linear now. In this case, we have the expected value of G of x and y, which is equal to the a times expected value of x plus B times expected value of Y and C. Actually, that is simple, right? Because we are working with the probabilities. So instead of X, we will just use the expected value of X, because that is the probability lecture, and the X value is not constant. They depends on some probabilities, right? That's why we are using the expected values. Another way to say it is, if G, the function, is linear, we have the expected value of G of X and Y actually equal to the G of expected value of X and expected value of Y. So, which is the expectation, we can conclude that the expectation is the linear operator. Okay, we can distribute that one. So let's look at the proof of that one. Let's say what we are saying the expected value of G of X and Y, which is equal to G of expected value of X and the expected value of Y. So we say that these two is same, right? And also we say the expectation is the linear operator. Let's look at the proof of that. Let's say which is the G of X and Y. So the expected value of G of X and Y. So in this example, the expected value of AX plus BY plus C. So which is equal to double sum AX plus BY and plus C times the corresponding probabilities, right? Because that will be the expected values, right? So I can just distribute these probabilities inside of the parentheses, and I just split that summations over this sums. So that will be the double sum AX P of X and Y plus BY times P of X and Y. So I will just multiply this one, and this one, and also because of the summation, I will just split them. And the last thing is C times double sum C times P of X and Y, right? Okay, now let's look at this guy first. Okay, which is this guy is not depends on Y. So I can just take this here. That will be sum of AX for all possible X times sum of the P of X and Y for all possible Y, right? And I will do the same thing for here. Like for this one, BY is not depends on X. So I will just change the order of the summation. That will be the summation of BY for all possible Y and the summation of X for PMF, for P of X and Y. And the same thing for this one. Okay. So let's look at this guy first. Which one? So this guy, okay? How can I make it more simple? What is this guy? This guy, the inside, the second summation. Here, I fixed the X values and I did the summation for all possible Y values, right? So remember from the first part, which is the marginal PDF of P of X, right? Okay, so which is equal to P of X. And same thing here, this part, I just fixed the Y values and go over all possible X values. So that is the equal to the marginal PMF of Y. Okay, so sorry, which is Y. So instead of this guy, I can write this. Instead of this, I can this. And also here, the C can go outside the summation, double summation, because that is not depends on X or Y. And all possible, the summation of all possible X and Y values. which is equal to 1, right? Because of the normalization axioms. So this guy is actually equal to C. So that will be the C. So here, which will be summation of x, ax, px, x, right? And here will be by p of y, right? So a is not dependent on x, so it can go outside the summation, and it will be the summation x, x, px, x. Okay. What is that? So that is the expected value of x. That's why, which is equal to, this guy is equal to a times expected value of x, and this guy is b times expected value of y, and c. So what is the result? So the expected value of ax plus by plus c is equal to is equal to a times expected value of x plus b times expected value of y plus c. So that's mean the expectation is a linear operator. Okay, so that is the proof of that. So that is the proof of expectation is a linear operator theorem. Okay, so okay, for the next part, in the next part we will continue with some examples, and then we will discover some other topics. Okay, I'll see you in the next part.